This is episode 11, season 1 of AI, Frankly.
We're really glad you're joining us for this deep dive today.
If you haven't heard MCP 101 and 102 yet, go back and start there. Links are in the show notes at afrankly.com. This episode picks up where those left off.
Right. And we're diving right into the deep end today.
We really are.
We are entirely bypassing all the high-level theory for this session. So there will be no broad, philosophical debates about where the technology might be heading in 5 or 10 years.
Yeah, none of that today.
Today is exclusively about the reality on the ground right now. We're treating this as a pure, unadulterated lab report. Our primary source is this independent piece of research titled The Laboratory of Unsanctioned Integration, and we're going to cross-reference those findings directly with the official Claude Code documentation straight from a THRO pick.
Because we're coming to you today as tinkerers, essentially. We've been analyzing the lab notes, looking at exactly how these systems are being wired together, and we are here to share the raw results of a very specific, highly documented experiment.
Just the facts of the test.
Right. We want to look at the raw output, the unprompted actions, and the compound effect of chaining disparate systems together. No speculation, just the actual logs.
And to properly set the stage for this lab report, we have to start with the inciting incident detailed in the author's notes.
The 11 commit night.
Yes. They refer to it simply as the 11 commit night. And it serves as the perfect baseline for everything else we're going to discuss with you today.
It really does. So let's paint the picture of this scenario, because it's deeply grounded in the everyday reality of software development. It's late at night. The author is facing this highly tedious task, fixing a specific routing issue on a web project.
Something every developer dreads at 2 a.m.
Exactly. More precisely, they needed to correct a routing error on the About page of a site and ensure that a hero image fit properly into a newly designed container.
Right.
Now, for anyone who has ever touched front-end web development, you know the traditional sequence of events required to accomplish that. It is a grueling manual session of context switching.
Let's really break down that friction because it's important to understand what's actually being replaced here. Think about that traditional workflow. You're digging through nested file directories in your IDE, trying to locate the specific routing component.
Yeah, and you're checking your terminal logs because your local build is throwing errors.
Exactly.
Yeah.
Then you realize the image is the wrong size. So you're manually opening the image asset in a manipulation tool, checking the pixel dimensions, cropping it, exporting
that back into the correct asset folder.
Right. Then you have to go back to the code, check the routing paths again, update the metadata schemas across the project to match the new routes. And finally, after all that bouncing around, you stage everything in version control to push it.
You're constantly jumping between 4, 5, maybe 6 different interfaces.
The cognitive load of simply managing the tools often outweighs the actual complexity of the task itself. But this time, according to the research log, the author decided not to do it the traditional way.
They didn't. Instead of managing the context switching manually, they handed the wheel over to the system local. One plain English sentence. That is all they typed into the terminal.
Which was?
Quote, fix the routing issue on the About page and ensure the hero image fits the new container. End quote.
That was the entirety of the input.
That was it. And over the course of the next 3 hours, running entirely locally on a personal machine, the system went to work. And the logs of what it actually executed are what we need to focus on today. It didn't just write a few lines of JavaScript and stop waiting for the user to copy and paste them.
No, it took complete operational control of the environment. The logs show it navigating the file tree on its own to locate the components. It identified the specific hero image that was breaking the layout. Then it autonomously executed a command line image manipulation tool to crop that image to the correct proportions.
Without being told to open an image editor.
Exactly. After handling the asset, it tracked down the broken URLs that were causing the routing errors in the first place. It updated the metadata schemas across the whole site to ensure they matched the new routes. And finally, it actually scaffolded entirely new pages from scratch just to handle the redirected traffic properly.
And it packaged all of that work neatly into version control without any prompting. The result of those 3 hours of autonomous local processing was 11 clean commits pushed directly to Git Hub.
And because the author had a continuous integration pipeline previously configured on that repository, Vercel deployed every single one of those 11 commits to production.
Every single one went live.
But here is the kicker, and this really is the only story we're focusing on today. Look at what actually happened in that scenario. 3 entirely separate systems were acted upon. The local file system, the version control system, and the deployment pipeline.
Right?
But there was zero audit trail for the decision-making process. Zero tickets were filed in any project management system. Zero formal change requests were opened. It just went.
One plain English sentence, and the infrastructure shifted.
Right. To properly analyze the mechanics of this lab report, we need to deconstruct the boundaries of that specific 11 commit night first.
Let's do that. Because that 3-hour session was conducted in a highly constrained environment, we can think of it as a safe zone, essentially. The tools it was using were personal local tools. The repository was a personal repository.
The entire operation was running on a personal machine equipped with a local Git instance.
Yes, and the communication between the AI and those local tools was handled via standard I/O transport. Let's break down that term for a second, standard I/O transport. What does that actually look like under the hood? Like, how is the AI actually talking to the computer in this safe zone?
So standard I/O, which stands for standard input and output streams, is the foundational communication layer for local processes on any computer, whether it's a Mac, a Windows machine, or a Linux server. When you open a terminal and type a command, the text you type is the standard input. When the terminal executes that command and spits text back at you, maybe a success message or an error code, that is the standard output.
Okay.
By connecting tools via standard I/O transport, Claude Code is essentially acting as a highly capable, tireless operator sitting directly at your keyboard. It formulates a command, pushes it through the standard input, the local machine executes it, and then the machine pushes the result back through the standard output.
So it's a completely closed loop. It reads the output, processes it, and decides on the next action based entirely on what the terminal just told it. It's not reaching out to the open internet to find a solution. It's relying on the local environment and its own internal weights to navigate the problem.
Precisely. If it tries to run a build command and the terminal throws an error about a missing dependency, the system reads that standard output, recognizes the error, formulates a new command to install the missing dependency, pushes that through the standard input, and tries the build command again. It is a highly restricted, iterative loop.
And the operational shift this represents is fundamental. If you think about the history of computing, we are all deeply accustomed to imperative commands. Telling a computer exactly how to do a task, step by step, line by line, open this file, change this specific variable on line 42, save the file, run the build script.
That is imperative. You're dictating the exact mechanics of the execution.
Exactly. What the 11 commit night demonstrates is the complete transition to declarative intent. You state the end goal, fix the routing issue. The system then takes that declarative intent and determines the optimal execution path to achieve it.
It decides entirely on its own whether the next logical step is to write a Python script, execute a pre-installed image manipulation tool, or parse through complex next.js routing files.
It chained those disparate actions together within that closed loop because it understood the intent, not just a list of instructions.
It is a highly efficient sequence, and the compound effect of chaining those actions together autonomously is undeniable. But as the author notes in the research, this was just the prologue.
Right, the baseline.
This was the safe, local sandbox where the blast radius was limited to a single hard drive. And that brings us to the real turn of this deep dive, leaving the local environment entirely.
This is where the architecture of the experiment scales up significantly. The baseline established that the model can successfully execute declarative intent across local files using standard I/O. But the core question driving the laboratory of unsanctioned integration was this: what happens when we leave the safety of those personal local tools and wire in strangers' tools on public servers via HTTP transports?
That is the frontier. And the shift in the potential blast radius here is immense. When you are operating via standard I/O on your local machine, you're manipulating local states. If the system hallucinates or makes a destructive error, it breaks a local file on your hard drive.
You can usually recover from that.
Right. But the moment you connect a remote server via an HTTP transport, you are no longer manipulating local states. You are executing state changes on third-party infrastructure.
You're taking those same autonomous chained actions and sending them as authenticated payloads across the open internet to servers you do not control.
Yes. To test the system's operational birth in this new, high-stakes context, the authors set up a very specific lab environment. They decided to wire in 3 external servers simultaneously to observe how the system managed multiple remote tool sets.
And they were very specific about which ones they chose.
They chose 2 official vendor servers, meaning the integration was built and maintained by the companies that own the platforms themselves, and 1 community-maintained server, which is an integration layer built by an independent developer.
Before we break down those 3 specific servers and what happened when they were connected, we need to address a major piece of technical friction that occurs when you start wiring in multiple platforms like this. Because according to the official and HRIC documentation, you can't just plug in an infinite number of servers without consequence. The sheer scale of the data these external servers inject into the system is massive. We are talking about JSON schemas.
It is a critical architectural constraint that dictates how these systems actually function in practice. When you connect a server via an HTTP transport, it doesn't just give the AI a simple URL and a list of tool names. It hands the AI a highly detailed, deeply nested JSON schema.
Right.
This schema describes every single tool available on that server, exactly what parameters each tool requires, what data types it accepts like strings, integers, or booleans, what fields are optional versus required, and exactly what the expected output data structure looks like.
It's basically a massive, dense instruction manual for how to speak to that specific server. And when you connect one server, that JSON schema might be a few thousand tokens. It's manageable. But when you wire in 3 or 5 or 10 complex enterprise platforms simultaneously, you run into a very real problem: context window saturation.
If the tool definitions consume too much of the AI's available context window, the reasoning capacity of the model begins to diminish rapidly. You experience severe retrieval drop-offs.
Because it's trying to hold too much syntax in its short-term memory.
Exactly. The model gets overwhelmed by the sheer volume of available parameters, endpoints, and data types. And it can actually lose the thread of the user's actual declarative intent. The official documentation explicitly warns about this degradation if schemas exceed 10% of the total context window.
To put that simply, it's like handing someone a 10,000-page manual for every single tool in a massive hardware store when all they did was ask you to hang a picture frame. They'd freeze up trying to cross-reference everything.
That's a great way to put it.
So how does the system actually handle this in the lab setup? If all these massive schemas from 3 different enterprise platforms are being wired in simultaneously, why doesn't the system just collapse under the weight of its own tool set?
It relies on a highly dynamic mechanism called the tool search router.
Okay.
Instead of forcefully loading every single tool schema into the active context window at all times, the system acts more like a semantic index. When the user submits a declarative prompt, the tool search router evaluates the core intent of that prompt.
Okay, so it looks at what you actually want to achieve first.
Exactly. It then mathematically searches the index of all available tools across all connected servers. It calculates the semantic relevance of each tool to the prompt and dynamically loads only the specific schemas that are mathematically necessary to accomplish that immediate intent.
Let me make sure I'm tracking this. So it actively filters the noise. If I ask it to check my calendar for next week, the tool search router ensures it isn't simultaneously loading the massive complex schema for managing cloud infrastructure deployments, which prevents the model from getting confused by irrelevant parameters.
Exactly. It mitigates the token bloat autonomously. It acts as an intelligent gatekeeper, allowing the model to maintain deep, focused reasoning capabilities on the task at hand, while still having theoretical on-demand access to hundreds of different endpoints across multiple servers.
And with that routing architecture in place to keep the system focused, we can look at the specific lab tests the author ran on the 3 selected servers. Let's dive right into server number 1. The official GIT Hub implementation.
This is a robust, highly capable integration. Because it is an official vendor server, the schema is deeply integrated into the platform's core architecture. The capability here extends far beyond simple, high-level read access.
It's not just looking at a static web page and summarizing the text.
No, the schema allows the system to perform deep, authenticated read and write access directly against the repository's underlying data structures. It can parse entire code bases, file by file, stage complex, multi-file changes, open pull requests, and if authorized by the user's credentials, merge those pull requests directly into the main production branch.
It essentially becomes a full-fledged, autonomous participant in the version control workflow. For the lab test, the author took a measured approach to start. They configured the Git Hub server for read-only access on a test repository.
They wanted to observe its analytical parsing capabilities before giving it write access.
Exactly. And the prompt they used for this test was a very basic routine request. They simply typed, "Summarize the last 10 commits."
A completely standard instruction for any developer catching up on a project after a few days away.
And the expected output was straightforward. A bulleted list of recent changes pulled directly from the commit messages. And the system did provide that summary. It parsed the text and returned the list. But the logs show that it then did something completely unprompted, something the author had not asked for.
This is the detail that really stands out in the report. After delivering the requested summary, the system flagged a specific pattern. It noted that 2 separate commits had touched the exact same file within a 24-hour window, and neither of those commits had a corresponding issue reference attached to them.
We have to analyze the underlying mechanics of how it arrived at that unprompted conclusion, because it is vital to understand that the system didn't develop spontaneous human intuition.
Right, it didn't just guess.
It performed rigorous pattern matching based on the definitions provided in the tool's schema and its underlying training data.
The Git Hub server schema, combined with the model's foundational knowledge of software development life cycles, contains strong structural definitions of what constitutes a well-formed, healthy repository history. It expects, mathematically speaking, the code changes map back to documented issues or tickets.
So it's reading the environment based on a defined set of best practices for version control. It knows what good looks like.
Yes, it parsed the raw Git metadata, the timestamps of the commits, the specific file paths that were altered, the author IDs, and the commit text itself. It processed all of that structured data to generate the simple summary you asked for.
Right.
But while processing it, the probability weights of noting a structural anomaly specifically, the missing issue IDs on highly concurrent changes to a single file were high enough to trigger a secondary response. It volunteered the anomaly because it recognized a mathematical deviation from the expected shape of good version control hygiene.
So from the user's perspective, sitting at the terminal, the system just performed a spontaneous code review and a process audit.
Essentially, yes.
It pattern matched the metadata, realized 2 developers were silently altering the exact same file without any corresponding documentation or tracking, and surfaced that operational friction, all from a simple prompt that just asked for a summary of the latest changes.
Functionally, it's performing an administrative audit. It demonstrates a deep understanding of the semantic meaning behind the Git metadata, recognizing that 2 undocumented changes to the same file in 24 hours often indicates a communication breakdown or a merge conflict waiting to happen, not just reading the literal text of the commit messages.
Which brings us to server number 2 in the lab report. N8. This is the official automation layer.
If the Git Hub server test was about state analysis and code manipulation, the N8N server test is about operational momentum.
Momentum, right?
N8N is a foundational node-based tool for complex system automation. It allows users to visually chain together different APIs and services, and this specific server integration is structurally distinct from simply telling an AI to write a Python script to ping a random API.
Let's really clarify that distinction because it is important. Why is using the N8 on server any different than me just telling an AI to write a quick script that sends an HTTP POST request to a specific webhook? Isn't that doing the exact same thing?
The difference is visibility and context. Normally, if an AI wants to trigger an external automation via a webhook, it's a blind handoff. It formats a payload, throws it at a URL, and hopes the receiving end knows what to do with it. It has no idea what happens after the webhook receives the data.
It's just firing and forgetting.
Exactly. But by connecting the official N8N server, the system interacts directly with the N8N execution engine itself. It doesn't just know that automations exist, it can see the full internal structure of the entire workspace.
Okay, wow.
It sees every available workflow, the exact input parameters required to trigger each specific node, and the expected JSON data structure that each workflow will output upon completion. It has a complete map of the operational layer.
So it acts as an intelligent orchestration engine, not just a trigger mechanism. For the lab test on this server, the author configured 3 distinct pre-built workflows in the N8N instance. Workflow 1 was set to query a database to retrieve the current project status.
Workflow 2 was configured to take text, format it into a specific layout, and send a Slack message.
And Workflow 3 was designed to create a calendar event for a team meeting. And the prompt the author fed into the terminal was simply, update the project status, and notify the team.
Think about the manual interpretation required for that instruction. You have to understand that the phrase update status implicitly requires fetching the current state first before you can update anyone. You have to understand that notify the team requires selecting an appropriate communication channel, like Slack, and drafting a coherent message based on that status.
Based on the logs and the research, the system triggered all three of those pre-built workflows in rapid sequence.
And it passed the data payloads between them seamlessly. It didn't just run them in isolation.
But the most crucial data point in the log here is that it did not pause for confirmation at any point during the sequence.
It did not. It mapped the declarative intent notify the team against the available schemas provided by the N8 server. It deduced the logical chain of execution required to fulfill that intent.
So it realized that the JSON output from the database query workflow was the mandatory input required for the Slack formatting workflow.
Yes. It executed the first workflow, ingested the resulting payload, fed it directly into the second workflow, executed that, and then deduced that creating a calendar event was the logical resolution for the remaining intent of the prompt, ensuring the team was actually brought together to discuss the status. It acted entirely autonomously because the tool scheme is aligned sequentially with the prompt's implied goal.
It didn't ask for permission. It just fetched the data, formatted the Slack message, fired it off, and booked the meeting.
That is an astonishing level of operational autonomy. It looked at the complex resources available, understood exactly how they fit together structurally, and executed a multi-step pipeline without needing explicit routing instructions for each individual node.
Which leads us perfectly into server number 3. Notion, the community-maintained server.
The inclusion of the Notion server in this specific lab report is vital because it addresses a fundamental limitation in interacting with large language models. Context window amnesia.
Yes, the ephemeral nature of these chats.
Exactly. When you use a standard chat interface, the session completely resets when you close the window. The AI loses all memory of previous interactions, decisions, or established facts. But integrating the Notion server provides a persistent, long-term structured memory bank that survives the ephemeral conversation window.
It gives the system a continuous, stable environment to reference. It can read and write to a database that doesn't disappear when the terminal closes. Now, it is worth highlighting that unlike the first two servers, which were official vendor releases, this was a community-maintained integration.
It wasn't built by the vendor, but rather an independent developer who wrote the translation layer to interface with the Notion API.
Which means the system is relying on an unofficial schema definition to understand the environment. It has to interpret the data structures as defined by a third party. For this test, the server was connected to a standard Kanban board in Notion. This board featured the typical columns you'd see in any Agile project: backlog, in progress, in review, and completed.
And the prompt the author used was entirely passive. They didn't ask it to move a card or update a status. They simply typed, "What do you see?"
A completely open-ended instruction. They just asked it to parse the persistent environment and report back. And the output was fascinating. It first rendered a structured markdown summary of the board, neatly listing the tasks in their respective columns.
But then it went a step further, just like it did with GitHub.
Yes.
It analyzed the state of the board based on the raw timestamps embedded in the Notion JSON payload.
It processed the temporal data.
The system noticed that a specific task sitting in the In Review column had an unchanged timestamp, indicating it had sat untouched for an entire week. It recognized this as a deviation from expected workflow velocity.
Yeah.
A task marked In Review should inherently be an active, short-term state.
Right.
So noticing this friction, it volunteered a solution. It offered to ping the task owner for an update or automatically update the status field to blocked.
Okay, wait, let me make sure I'm visualizing this right. The Notion server isn't just taking notes or reading text, because it can read the metadata, the literal integer timestamps of when a card was last moved. It's acting like a project manager noticing a sticky note has been gathering dust on a physical whiteboard for a week.
That is a highly accurate analogy. It read the environment, understood the workspace context and the operational definitions of those columns, and offered administrative upkeep without any explicit goal being defined in the prompt. It identified a logical inconsistency in the persistent data, a task marked In Review that wasn't actually being actively reviewed based on the temporal data, and proposed an actionable fix using the tools available in its schema.
We're seeing a distinct, powerful pattern across all three servers in these isolated tests. Pattern matching in GitHub leading to a spontaneous process audit. deductive sequencing in AIT-on, leading to autonomous automation execution without confirmation, and temporal analysis in ENOSHUN, leading to proactive workspace administration.
Which brings us to the climax of the lab report, the ultimate stress test, the moment of convergence.
This is where the architecture is pushed to its functional limits. The author took all three of these servers, the official GIT Hub server, the official N8N server, and the community-maintained NOcean server, and wired them in simultaneously via their respective HTTP transports.
The local system now had direct, concurrent access to version control, operational automation, and persistent project memory. It's looking at the entire operational stack at once.
And the single prompt they used to test this converged environment was deliberately, almost aggressively ambiguous. They typed, "Review the project status and tell me what needs attention."
A prompt like that offers absolutely zero routing instructions. It doesn't specify if the status lives in the NOcean documentation, the GIT Hub codebase, or the IT execution logs.
It requires the system to determine where to look, and how to logically compare the findings across entirely different platforms.
The author notes that after hitting enter, the terminal just sat still for 60 seconds, a full minute of processing time. Let's break down what was actually happening in that 60-second window, because it requires immense computational effort.
Let's hypothesize the chain of API calls and internal reasoning required to process that ambiguous intent across three disparate platforms. Because during those 60 seconds, the tool search router is working heavily.
Very heavily. The system likely began by querying the NOcean server to understand the intended state of the project. It pulled the massive JSON payload of the Kanban board to see what tasks were documented as in progress, what was blocked, and what was completed.
Then it queried the GIT Hub repository via its read schema to understand the actual compiled state of the codebase. It pulled the recent commit history, the branch structures, and the dependency files.
Finally, it queried the N8N instance via its transport to understand the operational state. It pulled the execution logs of the active workflows to see what automations were actually running.
So it is actively pulling down these three massive, distinct data models. It's loading the documentation state, the code state, and the operational state into its context window, actively managing the token bloat.
And then it has to synthesize them. It has to cross-reference them to find the hidden friction points that really exist in the gaps between the platforms.
It's comparing the intended reality against the compiled reality and the operational reality. And the output the terminal finally returned after that 60 seconds was a prioritized list of three specific findings. Let's go through the output, finding by finding, because the mechanics of each are vital. Item 1. It identified a stale dependency in the GIT Hub repository, and it cross-referenced that finding with the NOcean payload to prove that no maintenance ticket existed for it.
The mechanics of that single finding are deeply complex. It parsed the dependency files, likely a package.json or similar manifest in the GIT Hub payload. It recognized a version mismatch or an outdated timestamp indicating a stale library, and flagged it as an anomaly.
But it didn't stop there.
It didn't. It then held that code-level anomaly in its context window while it searched the NOcean Kanban payload. It looked for any task description or title that matched the stale dependency it just found. When it found none, it synthesized an entirely new conclusion. There's a technical deficit in the code and a corresponding documentation deficit on the board. It proved a negative.
Item 2. It pointed out a missing task in NOcean. It saw a recently merged feature branch in the GIT Hub commit history, and it inferred that a corresponding documentation task was missing from the Kanban board.
Again, it is bridging operational gaps. It understands the software development lifecycle defined in its base training. Code merged to a main branch usually requires documentation updates, release notes, or stakeholder communication.
It saw the merge event in GIT Hub. It saw the absence of any task related to release notes in NOcean. It inferred the missing workflow step and flagged it for the user's attention.
And item 3, it flagged a workflow failure in N8N. It noticed that a weekly reporting automation hadn't run in 2 weeks, despite its expected cron schedule explicitly stating it should run weekly.
Did it figure that out from the logs?
It parsed the configuration schema of the N8N workflow to read the cron schedule, which is a specific syntax like 000, indicating a weekly run. That is the intended operational state. It then parsed the actual execution logs returned by the server, the actual operational state. It mathematically compared the timestamps of the last successful run against the current date, noted the 2-week gap, and reported the failure, recognizing that the actual state had deviated from the intended state.
One deliberately ambiguous sentence. Review the project status and tell me what needs attention. And the system analyzed a stale code-based dependency, a missing documentation workflow, and a broken automation schedule across 3 separate external platforms without being explicitly told how to navigate any of them.
This convergence represents a profound paradigm shift in how we must categorize this technology moving forward. The word assistant is now completely inadequate to describe this architecture. An assistant implies passive dictation.
You tell an assistant to schedule a meeting, and it uses a specific calendar tool to do exactly that and nothing more.
But this isn't passive dictation. This is a synthetic infrastructure manager. It is actively bridging the operational gaps between version control, project management, and execution layers. It is managing the infrastructure by finding the inconsistencies between the disparate platforms that human operators typically miss.
It acts as an autonomous synthesis engine. When a single command line interface can parse your source code, realize your external project board is out of date, and identify a broken operational pipeline simultaneously, all from an ambiguous prompt, the definition of the tool has fundamentally changed. We're no longer talking about a chatbot. We're talking about an operational overlay.
Exactly.
Okay, I'm putting us on a strict clock here. We are only going to spend 90 seconds on the governance side of this because we want to get back to the tech, but we absolutely have to address the elephant in the room: authorization, the responsible footnote, glasses on in, starting the timer.
The tension here isn't about the model making a technical error. In the lab report, it executed the logic perfectly across all 3 platforms. The tension is entirely about authorization and the enterprise reality of how these transports function. Every single ADAN workflow it triggered, every GIT hub read request it made, and every NO shun query it executed was attributed directly to the personal API keys and OAuth tokens of the user sitting at the terminal.
The logging is completely opaque. To those external systems, it looks exactly like you manually typed every single command and executed every single API call.
Exactly. One user sitting at a terminal just became the entire change management record for the organization. So before connecting any tool, especially via an HTTP transport, you must apply the rule of 3.
Question 1. Who built the server? Is it an official vendor implementation with strict security standards, or a random repository maintained by a stranger on the internet?
Question 2. What do they actually log? Are your JSON payloads, your proprietary code-based snippets, and your sensitive project data passing through a proxy server you do not control before reaching the final API?
And question 3. Whose credentials does the execution actually run under? If the model autonomously decides to drop a row in a database because it inferred the data was stale, whose name is on the audit log, taking the blame for that destructor action?
That's the core risk.
All right, the clock is up, glasses off. We are moving immediately past the risk. We acknowledge the governance gap is massive, but the tension of this lab report is the sheer capability of the architecture, and that is what we want to focus on as we wrap up.
Which brings us to the Tinkerer's Lab. Try this yourself.
Because the most significant aspect of this entire paradigm shift is the accessibility. We operate on what we call the Minecraft PC standard. If your personal machine can run a modern web browser, and you have access to an any mean instance, whether that is running locally or cloud-based, you can run this exact stack tonight.
The barrier to entry for this level of synthetic infrastructure management is essentially gone.
You don't need a massive enterprise server rack. You don't need a dedicated DevOps team. You just need a terminal and an understanding of how to configure a transport layer. So we have a 30-minute safe lab for you, the listener, to run step by step. We want you to experience these mechanics firsthand.
Step 1 is to isolate the variable. We want to observe the parsing logic without any risk of destructive actions. So set up one single, completely harmless test workflow in your ADAN instance. For example, configure a simple workflow that pulls a public weather report based on a city input. Ensure there's absolutely 0 production data, 0 sensitive API access, and 0 write capabilities in that specific workspace. Keep it entirely isolated.
Step 2. Initialize your interface and connect the server via your terminal. You will use the standard command format to add the man-ADAN server, pointing it to your specific URL. Pay very close attention to the configuration files it generates in your local directory when you execute that command. Open those files in a text editor.
You want to understand how the system actually stores the transport definitions. You will see the raw JSON schemas being defined. And then, step 3, the prompt. Go to your terminal and simply ask, what workflows are available?
And this is the crucial part. Observe. Instruct yourself to watch closely. Don't just read the final text it spits back at you. Watch how it structures the response in the terminal. Watch how it parses the parameters of your specific weather workflow.
Watch how it infers the underlying purpose of that specific API connection. And inevitably, watch how it offers to execute it for you, or suggests a modified use case you hadn't explicitly programmed into the node.
Seeing the JSON payloads transfer in real time, watching the tool search router identify the weather schema and load it into the active context window teaches you significantly more about this architecture than reading any piece of documentation ever could.
You have to watch the theoretical become practical to truly grasp the operational shift.
So as we reach the outro of this lab report, what is the final verdict on the laboratory of unsanctioned integration?
For the tinkerers, the verdict is that this ecosystem is fully functional right now. It is not hypothetical, it is operational. But the technical advice is to start exclusively with official servers from vendors you already trust. Utilize the official implementations for Git Hub and 8 and Ocean. Get used to how the standard I/O and HTTP transport protocols function in a safe, verified manner before experimenting further with community builds.
And before we sign off, we want to leave you with one final provocative thought to mull over during your own 30-minute lab tonight. Something that builds on everything we've unpacked here about inference and autonomy.
Think about the convergence test we just analyzed. We watched the system autonomously infer a missing documentation task in a persistent memory database based purely on reading a code commit timestamp in a separate version control system. Now, project that capability forward. As these schemas inevitably expand, and as the tool search routers become capable of handling thousands of distinct endpoints concurrently without token bloat, what happens when the system begins identifying structural gaps in your entire operational architecture?
What happens when it doesn't just find a missing task, but infers a missing capability entirely?
How long until it recognizes an operational inefficiency and autonomously offers to write the integration script, generate the required JSON schema, and configure the transport layer for a tool you haven't even installed yet? That frontier where the system actively architects its own toolset to solve inferred structural gaps is much closer than we think.
You can find everything at afrankly.com. Subscribe free on Substack, watch on YouTube, and listen on Apple Podcasts and Spotify. Just search AI Frankly.